In this Organic Chemistry 1 screencast, we're going to look at the following prompt. Given the molecular formula of C6H14, draw all the possible constitutional isomers. Then we're going to use the concept of uniqueness to determine how many carbon and hydrogen types there are in each of them. Along the way, we'll also use some fundamental nomenclature rules to name each isomer as well. So given the molecular formula C6H14, we know immediately that that is a hydrocarbon. There are no heteroatoms contained in the molecular formula. And the other thing we want to look at is the general hydrocarbon alkane formula of CnH2n plus 2. What we want to do now is determine if this molecular formula is fully saturated, and for n equal to 6, we can plug that into that general formula, H, 2 times 6 plus 2. We're going to find that that does equal C6H14. So what that is telling us is each carbon atom is fully saturated, or will have 4 sigma bonds. Before we move on with solving this problem, why don't you pause the video, take a few minutes to work through the problem, and see how many isomers you can come up with, and what the unique type of carbon and unique type of hydrogens you find for each isomer. So let's go ahead and start with the longest chain length of C6. And what I mean by that is we're going to bond each carbon atom in a linear fashion. So we'll go ahead and start doing that. So there's 2, 3, 4, 5, 6. So if we number that, we see we have 1, 2, 3, 4, 5, 6. This compound is called hexane. And that's the linear C6 hydrocarbon alkane. In determining the unique types of carbon and hydrogen, we have terminal methyl groups. Those are CH3 groups. I'm just going to underline them in blue. So those are the same type. Then if you look at 2, 3, 4, and 5, those are all CH2 groups, but they're not the same type of CH2 group. So 2 and 5 will be the same type. And then 3 and 4 will be a different type, but they're also the same. So ultimately, we end up with 3 unique type of carbon. We have 1 and 6, 2 and 5, 3 and 4. Now the same will hold true for the types of hydrogens for hexanes as well. So the methyl groups at 1 and 6 are the same. So there's 6 of those. So let's capture that in terms of a ratio. So we have 6. The CH2 groups, 2 and 5 are the same. That's 4. And then 3 and 4 are the same, so that's 4 as well. So notice that the sum of those is equal to 14. And so from this ratio, the total we get is called the integration. So this ends up being 3 unique sets of H as well. So the reason we're doing this type of analysis is that it's useful for differentiating isomers, specifically constitutional isomers, which have the same molecular formula and therefore the same molecular weight. So with C6H14, we can't possibly draw any more linear C6 isomers. So we're going to knock it down to C5. So we're going to draw a 5-carbon chain. We have 1 more carbon to put on there. So let's go ahead and first label this chain 1, 2, 3, 4, 5. So from here we can see that we have 1 more carbon. We can't put it positions 1 or 5 because then we're just making a 6-carbon chain again. So we have to start at an internal position. And the easiest thing to do is just start at position 2. So we do that. Now we've accounted for all 6 carbons and all 14 hydrogens. So to name this compound, it's going to have the base of pentane. That's the longest chain, which I'll circle in green here. So the base parent is going to be pentane. And so the thing that is hanging outside of what I just circled is called a substituent. You can see that that substituent is located at carbon 2. So it's located at carbon 2, and it corresponds to 1 carbon. A 1 carbon unit is methane, but because this is a substituent, we're going to abbreviate methane to methyl. So this is going to be 2-methylpentane. So that's all one word. So now we're going to do the carbon analysis, and I'm going to use sort of a different technique to do that, where I label each unique carbon as sort of a circle or a triangle or a shape. So it's another way of visually determining that. So when we're looking at this chain, we see the 5-carbon chain. We run into a methyl group at position 1. So I'm just going to put a little dot there saying that's a unique carbon. We go to carbon 2. That just has a CH group connected to 3 different carbons. So let me put like a little triangle there. That also bears a CH3 group. And so you can see that that CH3 group is equivalent to the carbon that's at 1. So we can put a little dot there. As we go to carbon 3, that's a CH2 group. That's unique from what we've seen before. And we'll put a square. Carbon 4 is a CH2 group, but it's not the same as the CH2 group at 3. So maybe we'll put a little parallelogram. So far we're up to 1, 2, 3, 4 different types of carbon. And then 5 is a CH3 group that is unique from the other CH3 group, so we'll put a little asterisk. So total in this molecule we have 5 unique type of carbon. So already we've differentiated hexane from 2-methylpentane based on the unique type of carbon. For the unique type of hydrogen, they're pretty much going to track what we've already seen. There's going to be 5 unique type. The ratio of this is going to be 6. Those are the equivalent methyl groups. To 3, the second type of methyl group. Then we have the 2 type of methylene groups, and then the methine group is 1. And again, this is going to equal 14. That's what you're looking for at all times, is that the sum is equal to what you observe in the molecular formula. Now keep in mind, for the unique type of carbon, it can be less due to symmetry. So when we drew this first C5 isomer, we put the methyl group at position 2, but what about position 3? We can do that as well. So that's another isomer of C6H14. So there it is. And we're putting the methyl group at position 3. So this compound is going to be called Three-methylpentane. If you look at it, there's a plane of symmetry about that C3 carbon. So you can see that carbons 1 and 5 are the same. 2 and 4 are the same. 3 is unique, and then the methyl group at position 3 is its own unique carbon. So total we have 4 unique type of carbon. So again, just to show that visually, these are equivalent, these are equivalent, then 3 and the methyl group at 3 are both different. So we have 4. So far hexane had 3, 2-methylpentane had 5, 3-methylpentane has 4. So this is also going to track with the number of proton signals. So we have 4 unique H types, and that's a ratio of 6. So we get that from 1 and 5 being equivalent. The methyl group at position 3. 2 and 4 being equivalent. Those CH2 groups, there's 2 of them, so that's 4. And then the methine group at carbon 3. Again, that equals 14. At this position, or at this time, we've exhausted all the C5 isomers. You can't put the methyl group at position 4 because then you're really just making 2-methylpentane again. So what we do now is move down to the C4 linear hydrocarbon, and these are going to be butane derivatives. So there's 4, 1, 2, 3, 4 carbons. Now we have 2 methyl groups to install in here. And again, when you're doing this type of analysis, you can't put those groups at the terminal carbons because then you're just making the next higher chain, which we've already done. So we're going to start at the internal, start at position 2. So there's a carbon. We have 1 more to take care of, and let's do this in a logical fashion. So we'll just put it again at the second position. So we're going to name this as a butane derivative because that's the longest chain. And then we see at position 2 there is branching. There are 2 methyl groups, so we call this 2,2-dimethylbutane. So because there are 2 methyl groups, you have to specify where both of them are. They both happen to be on position 2. That's where the 2,2 comes from. The dimethyl says that there's 2 of them, and the methyl is the actual substituent. So now let's use that same sort of color analysis with a shape here as we go along. We start at position 1. We see a methyl group. We go to carbon 2. That's a quaternary carbon. There's no hydrogens. Now we look at those substituents bonded to carbon 2. We see that they're methyl groups as well. And so they're actually equivalent to the carbon that's at carbon 1. So we can put circles by them. So far we only have 2 unique type of carbon. We go to position 3. That's a CH2 group. That's its own thing. So we'll put a little square. Then we have a methyl group at carbon 4. And that is different from the first 3 methyl groups we saw, so let's put an asterisk. So total we have 4 unique type of carbon. So now you can see 2,2-dimethylbutane and 3-methylpentane both have 4 unique type of carbon. But what we'll find is that the unique type of hydrogens will be different, so that way we can differentiate them. So the answer for this one will have 3 unique type of hydrogen. And that's because if we look at carbon 2, that carbon is not bearing any hydrogens. So that immediately eliminates that as like a unique type of hydrogen. The methyl groups bonded to carbon 2. So there's 3 of them. That's going to give us 9 hydrogens. We have a methyl group at 4, that's 3. And then we have the CH2 group at carbon 3, so that's 2. And again, that sums to 14. So you can see that's how we can differentiate 3-methylpentane from 2,2-dimethylbutane based on the unique number of hydrogens. So we can continue on with the C4 chain. There's another isomer we can consider. There's our chain. Let's go ahead and number it so we're logical about how we follow this. So in the above example, we started putting those groups on at position 2. Let's do that again. So we'll put one there. Then before we put the second one on position 2, now we'll put the second one on position 3. So what we've made now is 2,3-dimethylbutane. And if we look at the unique type of carbon here, we go along the chain, we have a methyl group, position 1. Position 2, we have a methine, that's a CH. Then if you look, you have another methyl group at carbon 2. Go out to carbon 3, that's a methine. And then you're going to find that carbon 4 and the substituent at carbon 3 are the same. So essentially, all the methyl groups end up being equivalent. So there's essentially 2 unique type of carbon here and 2 unique type of H. The 4 methyl groups, that's 12, and then the 2 methine, that's 2, so that equals 14. So using this concept of uniqueness, we're able to differentiate the different types of constitutional isomers for any given molecular formula. So to summarize, in this problem, we've looked at C6H14, starting with the linear hexane chain, going down to C5 and C4. We've counted the unique type of carbon, unique type of hydrogen, determined their ratio, and essentially integration.